Okay, so in the last lecture we have discussed the Fourier transform, and we derived the two important relationship. One is Fourier transform, of a given signal x of t. It is denoted by x of j omega is equal to integral of x of t times e to the minus j omega t times dt, and the limit of integration is from minus infinity to plus infinity. And Fourier integral, that is inverse Fourier transform, also called inverse Fourier transform. And this is given by, you can get back your x of t from x of j omega. That's what we mean by inverse Fourier transform. 1 over 2 pi integral of x of j omega e to the plus j omega t times d omega. Now you are doing the integration with respect to omega, and the range is of course from minus infinity to plus infinity. Okay, now in this lecture what we will do is, we will look into the meanings of the coefficient density. By the way, this is called a coefficient density. So what is the meaning of the coefficient density? And also let us try to understand the similarities and the contrast between the periodic function and the aperiodic function. So this is what we are going to discuss in this lecture now, similarities and contrast, okay, between periodic and aperiodic. If the signal is periodic, what are the similarities, and if the signal is aperiodic, what are the contrast, dissimilarities in greater detail. Now after we studied this Fourier transform and the Fourier integral, now let us compare. Okay, so if you had a periodic function of time, say period t naught, periodic function of time with the period t naught, then you have the Fourier series representation, that is Fourier series coefficients Cn. Okay, so in general this Cn is a complex number. If it is complex, then this guy can be represented in terms of magnitude spectrum and phase spectrum. Any complex number can be represented in terms of magnitude and phase. And also we said that magnitude spectrum is an even function of what? Even function of n, and phase spectrum is odd function of n. Okay, therefore the x-axis is graduated in terms of say 0, 1, 2, 3 and so on. The left hand side minus 1, minus 2, minus 3 and so on. Therefore like this. Or you can also graduate the x-axis as this is 0, 1 omega naught, then 2 omega naught, 3 omega naught and so on. So n omega naught. Here the x-axis graduated in terms of n, and here in terms of graduated in terms of n omega naught. Both are same, and this is your mod of Cn. Therefore you can graduate the x-axis either in terms of n or in terms of n omega naught. Similarly, if you try to plot the phase, again you can choose n or in terms of n omega naught. And we said the phase spectrum is an odd function like this. and the magnitude is one second, I will come back. Okay, it is odd. So 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, and so on. And here let's say this is your C0, then C1, C2, like that, and here C minus 1, C minus 2, like that, C1, C2, all are magnitudes, and like that it goes both the left hand side as well as right hand side. Okay, please recall, just I am drawn some arbitrary waveforms. Now for a particular Cn, let me take this value for particular Cn. I have the corresponding phase also here. This is the phase. You put together these two components together will give me C minus 1, right, and e to the j times phi 1 and e to the j times omega naught, because it is omega naught, no, so I put omega naught here. Similarly, if you take this term C minus 1, then this is the magnitude and the corresponding phase is this one. So if you put together these two guys, then I will get C1 e to the minus j phi 1 times e to the minus j omega naught t. If you combine these two guys together, C minus 1, this is C minus 1 e to the minus j phi 1 e to the minus j omega naught t plus C1, this is wrong, this is C1 actually, okay, C1 e to the j phi 1 e to the, this is magnitude, by the way, this all are magnitudes, e to the j times omega naught t. Now this magnitude of C minus 1 is the same as magnitude of C1, so I can take this commonly outside, then you combine these two terms, e to the minus j, then within a bracket omega naught t plus phi 1 plus e to the j times omega naught t plus phi 1. So what is this? This is 2 times magnitude of C1 times cos of omega naught t plus phi 1. Okay, therefore how many terms do we have? We have 4 terms. For negative n we have 2 terms. These 2 terms for negative n, and these 2 terms for positive n. So in general what you can say is I have C suffix n mod of Cn for n greater than 0. Then second term is C minus n mod of modulus for n greater than 0, and also I have phi n for n less than 0 and phi n for n greater than 0. So I have 4 terms. Okay, you put together all these 4 terms and that will give rise to like Cn mod of Cn times e to the j times phi n e to the j n omega naught t plus Cn C minus n modulus e to the minus j phi n e to the minus j n omega naught t. Then you come this magnitude and that magnitude both are same as we did in the example. Then if you rearrange the terms, then 2 times cos of n omega naught t plus phi n. So the meaning of this negative frequency here, this negative frequency minus n omega naught is only, it means that This is the coefficient of jt term in the exponential representation. See, in the exponential representation, what we said, let me write down. X of t is equal to sigma n is equal to minus infinity to plus infinity Cn e to the j n omega naught t, right? Now, if you substitute n equal to minus value, n is equal to minus value, then what will you get? You will get c suffix minus n e to the minus j n omega naught t, right? Now, what you can do is, you can rearrange this guy as c minus n e to the n omega naught of jt. Okay, so minus n omega naught jt. Now, what is this minus n omega naught? This minus n omega naught is just a coefficient of what? Jt term in the exponential representation. Okay, even though these frequencies are negative, but if you combine this positive and the negative, okay, negative terms together, then it provides you a real frequency of n omega naught. Where is the real frequency? This is the real frequency. Okay, so this is a line spectrum, this one is line spectrum, both are line spectrum, and there will be frequency component present only at the discrete values along the x-axis, and they are all integral multiples of either n or omega naught, that is fundamental frequency. Okay, so as I said, the spacing between the two lines is omega naught. Okay, so that's all about your periodic case. So in the periodic case, so you have both positive frequency and negative frequency. If you look at negative frequency alone, it does not give any meaning. So the negative frequency always combines with the positive frequency, and finally you will get a like a real signal like this. So it's simply a mathematical representation. Now let us look at aperiodic case. Now in the aperiodic case, what is going to happen? Aperiodic signal. So please recall from the previous lecture that in the aperiodic case, we have same phenomena, okay, signal or same signal like periodic signal, but that lasts only once, it occurs only once. See, this is my periodic signal like this. This is periodic. Now the period is, let us say, t naught. Now what we are going to say is, again I am going to take the same signal, but the signal occurs only once, and it occurs after infinite duration. T naught goes to infinity. Okay, so minus d by 2 to plus d by 2, and this is a, and now this case is aperiodic. So that is the only one difference. In periodic you have many pulses which are occurring with a fixed time interval, but in aperiodic case also you have only one pulse, and that pulse occurs only once, that's all. It does not repeat itself. Therefore the period t naught tends to infinity. Now let me take an arbitrary signal. I don't know how, let us say the signal is maybe like this, some arbitrary signal like this. Like this. It occurs only once, and afterwards the signal does not occur. So therefore the period t naught goes to infinity. Let me say this is my x of t. The period t naught goes to infinity. Okay, and as we said, this will lead to a spectrum. That spectrum is called x of j omega, and we call that x of j omega that coefficient density. It is not simply coefficient, Fourier series coefficient or Fourier transform coefficient, it is coefficient density. And we also have associated with this, after all x of j omega in general a complex number, right? So this is associated with the magnitude spectrum and phase spectrum. Again the magnitude spectrum is an even function and phase spectrum is an odd function of, here even function of not n, in the previous case it is even function of n, look at here. Okay, we said see it is a function of n, but here it is not function of n, it is a function of omega, even function of omega, and this is odd function of omega, that is it. Because x of j omega is complex number, so therefore you have magnitude and angle associated with that, and this both magnitude and phase both are continuous. In the periodic case both are discrete, please recall. So magnitude it's a function of n or n omega naught, phase also function of n or n omega naught, and here this both magnitude and phase both are continuous, and this both magnitude and phase are discrete. You have only values at discrete points in the x axis. So this is the difference between your periodic signal and aperiodic signal. And the phase associated with x of j omega is phi of omega, it is a function of omega. There we denoted phi suffix n, and here we are using phi omega. So this is for Fourier series and this is for Fourier transform. This is for periodic signal and this is for aperiodic signal, and the magnitude is x of j omega, and here the magnitude is Cn modulus value. Now let me take the same signal . I am taking one arbitrary signal like this, let me call x of t, okay, and I am assuming that its spectrum is like this. I don't know, let us say like this. Like this, let me call this is my x of j omega magnitude, and as I said the phase spectrum should be an even function of omega, like this. This also omega and this also omega, and this is your phi of omega. So it is odd function, this is 0 0 like this. Okay, now we said this is the we said that coefficient density is an even function, right? So therefore it is an even function. And what does that really mean when I say coefficient density? When somebody says coefficient density, what does that really mean? If you look at small intervals, okay, very small intervals, let me enlarge this. If you take small intervals, let us say this interval is delta omega. Where should I write? And this interval is delta omega. You take small interval and you take the corresponding slice here also in the same frequency. This is again delta omega. So the magnitude spectrum and the phase spectrum together leads to a constituent of your x of t. What is that function? By the way, this is the coefficient density. That means over this interval delta omega, the density is, let us say this is center point. At the center point your density is, let us say x of j omega. Therefore the total magnitude is this center point take magnitude of that and multiply by delta omega. So that is your total area, that is the strength. And in the same interval you have the phase. What is that phase? That phase is e to the j times phi of omega. Okay, so it has the magnitude of this guy and it has the phase of that guy over the small interval. Say I cannot take a single point. At the single point the value is 0. Okay, in the continuous case, if you take the single point, that value is 0. I cannot say. So I need to consider only an interval. So that's why I took very small interval. Okay, so if you combine these two guys, then you will get x of j omega magnitude and the interval is delta omega. Then its phase is e to the j times phi of omega and multiplied by its exponent, time exponent e to the j omega t. So this is what we get from the positive frequency, positive omega. Similarly, for negative omega, you consider the same interval in the left hand side and you take this is a center point, then this is x of minus j omega, you take magnitude and multiply by the interval delta omega. Okay, now the corresponding phase you consider here, and this again omega, delta omega, and the phase is e to the j times minus j times phi of omega, right, and e to the minus j omega t. Okay, so if you combine this magnitude part and the phase part, this is delta omega and this is a magnitude part. You combine this magnitude part and this is phase part and this one is magnitude part. You take these two guys. So delta omega mod of x of minus j omega e to the minus j phi of omega, then you multiply its time exponential e to the minus j omega t. Where does this e to the minus j omega t come? Because in the integral you know, right, integration x of j omega e to the j omega t d omega 1 over 2 pi and this is your x of t. Recall this. Okay, so minus infinity to plus infinity. When you substitute this omega is equal to minus infinity to plus infinity, when you substitute omega is equal to minus, then you will get this minus value. This minus value you get it. So that's how this term comes. Okay, now what you do, add this positive component and the negative component. What is the positive one? The positive one is this guy and the negative one is this guy. You add these two guys together. So x of this is j omega, you take magnitude delta omega e to the j times phi of omega plus e to the j omega t plus this guy comes here, delta omega magnitude of minus x of j omega, then e to the minus j phi n, then e to the minus j omega t. Now the magnitude is an even function, so these two are equal, both are equal. Therefore, and this delta omega commonly you can take it outside. So delta omega times x of j omega magnitude, then within a bracket you have e to the j times, combine these two exponentials, omega t plus phi of omega plus e to the, combine these two exponentials, minus j times omega t plus phi of omega. Okay, now this is going to be 2 times delta omega x of j omega magnitude and then cos of omega t plus phi of omega. So even though you have components corresponding to negative frequency, when omega becomes negative, what it really means is for every negative frequency in the left hand side, every negative frequency here, you have a positive frequencies here. So this all are negative frequency and here you have positive frequency. Okay, and all together will yield a real function. That real function is given here, real function. So negative frequency and positive frequency, if you combine these two guys, then you will get a real function of time. And by the way, this function, this signal you can generate in the laboratory also, and this is a cosine function. Okay, so in this aperiodic case, if you look at every point on the x-axis you have a value. Okay, so in other words, what we are having here is at every given point of frequency in aperiodic case, if you want to know the amplitude is 0. If you take a single point, then the amplitude is 0. Okay, but if you take a small width delta omega, if you take a small width delta omega like this, oh my god. It went something wrong, 1 second. If you take a small interval, then the amplitude is 0. Sorry, if you take a single point, then the amplitude is 0. But if you take a small width along the omega axis, and if you consider this slice to be represented by a single frequency term at the center, then the amplitude of the particular exponential term will be given by magnitude of x of j omega times delta omega, and this magnitude of x of j omega is called a coefficient density. Okay, so in other words, if you recall, let us say x of t is a voltage waveform. Okay, then the dimension of x of j omega is in volts per cycles per second. Whereas in the periodic case, if x of t is a voltage waveform, the unit is volt, then Cn, your Fourier series coefficient, will be in volt. So there is no change in the units in the case of periodic signal, I mean in Fourier series. But in the case of Fourier transform, then the units are not same between the time domain and in the frequency domain. Okay, so in Fourier transform, let us say x of t is in volt, then this x of j omega will be volts per cycles per second. That means what? Volt per cycles per second. Therefore the second will come to the numerator. Volts times seconds. This is the x of j omega unit. But in the case of periodic case, in the case of Fourier series, then it is going to be like x of t also volt, then your Cn also in terms of volt. There is no change in unit. Okay, so this x of j omega gives the amplitude of each individual components. Sorry, the Cn gives the amplitude of each individual component. Okay, but whereas this x of j omega gives not the amplitude but magnitude density, and this one is magnitude density. here amplitude, individual amplitude, you can get it at n equal to at omega equals omega naught, because when I substitute omega, then omega naught, 2 omega naught, 3 omega naught. At each point, you know this exactly, you know what is the amplitude. So let's say this is 1 volts, this is 1.5 volts, like this. In between the amplitude is 0. It is a discrete spectrum. But in the case of Fourier transform, it is continuous. So at a single point, I cannot say what is amplitude. Okay, but if I take an area like that, then I can give you. That is why this is called a magnitude density. This function is, the y-axis is magnitude density. It is not magnitude, it is magnitude density function. Like it is something, if you recall from your applied mechanics course. Okay, so you have a beam here, and we have concentrated loads at let's say the loads are concentrated at, let's say here 50 kg and here let's say some 100 kg. Okay, this is one way of looking at it. And sometimes you have your distributed loads like this. Let's say the load is distributed along the axis. Let's say this is 1000 kg. Right? In the case of distributed loads, okay, in the case of distributed loads, what we say is so much kilogram per unit length, kilogram per unit length. Okay, so at any given point there is no load, but if you take a small interval and the total load in that interval will be density times the small elemental distance. But here you can say that at a discrete point my weight is 50 kg and my weight is 100 kg. So the similar kind of situation exists in the Fourier transform also. Okay, you take a small interval and you can find out what is the amplitude. If you take individual component, single component, then it has almost negligible amplitude. Negligible amplitude. You take a small point over a small interval along the omega axis. You can think of that this section, this is small interval delta omega. Okay, which has an amplitude like x of j omega in the small interval, then the interval is multiplied by delta omega. Okay, this x of j omega is called a density function. Let me write down here. This is density, and these two put together called total amplitude at that interval. Okay, so in this lecture and in the previous lecture, what we have done is we have demonstrated by taking the limiting case of Fourier series. We started from the Fourier series. We started with the Fourier series, and then we finally derived the Fourier transform. Okay, so when I say limiting case of Fourier series, what we mean by the frequencies becomes smaller and smaller, right? Omega naught becomes smaller and smaller, and then the period becomes larger and larger. So even an aperiodic case can be thought of as composed of number of different frequency components. In contrast to the Fourier series, which consents itself with a periodic case. Here we have frequency component. In Fourier transform, we have frequency component at every consumable frequency all along the omega axis, that is x axis, from minus infinity to plus infinity. This is my x axis. So the frequency exists at every point. But at single point their amplitude is their amplitudes are vanishingly small. So the amplitude at any given frequency is 0 because it is continuous. Any single point, the amplitude is 0. So what we really are, because it is a density function. So what we are really talking about is the amplitude density or the magnitude density, otherwise called coefficient density. So you can say amplitude density or magnitude density or coefficient density. And the coefficient density is we termed as like x of j omega. Okay, because this x of j omega is a function of omega, we would like to associate omega with that term in terms of frequency. Therefore, it is written as x of j omega. Basically, these two relations which are important. What are those two relations? One is Fourier transform x of j omega. Let me write down as a final point, minus infinity to plus infinity x of t e to the minus j omega t times dt. This is called a Fourier transform, and then x of t is equal to 1 over 2 pi integral of minus infinity to plus infinity, then x of j omega, then e to the plus j omega t times d omega. This is called inverse Fourier transform or Fourier integral. See, there is a additional scaling factor of 1 over 2 pi. Sometimes if you don't like that, then you can do the same thing. Now this time it is not going to be in terms of function of omega, it is function of f, e to the j times 2 pi f times t, then df. Both are same, identically equal. Okay, and both Fourier transform and Fourier integral, the limit is from minus infinity to plus infinity. Okay, and here we got 1 over 2 pi. In the other case, here there is no 1 over 2 pi. In the Fourier transform there is no 1 over 2 pi, but in the inverse Fourier transform we have 1 over 2 pi. Okay, so as I said, we got this 1 over 2 pi because we are defining the coefficient density as the amplitude per cycles per second, that is f naught, instead of omega naught. That means you always look at the function x of t is being composed of an exponential term, which is the function of this x of t. You can always look at as it is composed of an exponential term like this, e to the j omega t, which is a function of omega and t. Okay. Now what is the amplitude? The amplitude is x of j omega. Okay. Not only x of j omega times delta omega by 2 pi. That is why this 1 over 2 pi is coming. Okay. So what we have done in this lecture is any periodic function can be thought of as an infinite summation of elementary frequency components. So each with vanishingly small amplitude and with all frequencies present along the omega axis, that is x axis. Okay, so let me stop at this point. In the next lecture, we will discuss the properties of Fourier transform. Thank you very much.